Hello, everyone. Hope you're doing well. We have been on a little bit of a playground recently, trying out new things with this new tool that we have in our arsenal to work with, which is that of a metric space. We've talked about all of these different types of examples of metric spaces, convergence in terms of metric spaces, and finally, we've used that tool of convergence to talk about how we can show general notions of how to show something like little LP is itself a metric space. Now, we're going to be going through a lot of other examples at a kind of maybe a lower difficulty level than that particular example, but I want to keep referring back to some of those things back in that example, namely the importance of how we showed things like the triangle inequality for some of these sequences that had some strange types of definitions of metrics for each of these, namely little LP could have had any sort of uh, real number power as long as that value of p was greater than 1 defined in its particular formula, and that can lead to a lot of like different metrics on different spaces there, many of which are a little bit tricky to think or visualize of how these sorts of things work. So my encouragement to you is to go back and be looking at some of those methods and try keeping to make sense of them. We won't get into something of that level until the second half of this course. However, we are going to be seeing arguments where we do have to go through multi-step processes like this in order to prove a general result, a very strong result usually, after having proved several lemmas, kind of like in that sort of setup there. So hopefully seeing something like that and looking over it again and again helps make it seem like how mathematics works at this sort of level. We really are trying to use every single thing that we have available to us. This notion of integrating with respect to dx and dy when proving Young's inequality, for example, this interesting kind of numerical argument that came right before it, all together with the proofs of Helder's inequality and Minkowski's inequality that kind of used some little bits of shorthand here and there, something called the norm, as something to kind of build in there. Now, I'm going to be doing my best to take out the norm language in what is to come. And I've gone through and made sure in my notes that even though I'm sometimes taking from other sources that are utilizing this sort of norm language early, I'm saying let's keep that until we've really talked about what norms are. So you'll see that we talk about some things that when you come back later on, you'll be like, oh yeah, that's just the norm of this particular element. But we haven't gotten to that point yet because we're just focusing on metric spaces right now. We won't get to norm spaces until week 8. So instead, let's talk a little bit more about these metric spaces, continuity especially. So we've already talked about examples and convergence, and let's keep going and talking about how to show a function between two metric spaces is convergent. So far, we've been looking at the sets themselves. We've been looking at sequences inside of one set that is a metric space. And now today we are going to branch out into looking at functions between any two metric spaces. Now, this sort of definition is going to be very familiar to us. Notice here that the functions that we're looking at are not just functions into the real numbers, right? The metric function is a function into the real numbers. It takes 2 points inside of your metric space x, and it spits you out a non-negative number. But this is going to be a function f from x to y. Here, y, very much like x, is a metric space with its own metric on it. And we'll say that a function f from x to y is continuous at a point A inside of the set x. If for all epsilon greater than 0, there exists a delta greater than 0, such that the distance from f of x and f of a is less than epsilon whenever the distance between x and a is less than delta. Notice that if we just go through and replace x to be Rm, y to be r, and to put the metrics to be the standard metrics on these spaces, namely those having to do with the absolute value or Euclidean distance, then this is exactly our definition of continuity from before. We've only generalized it slightly to say that we can now be looking in between two different metric spaces inside of this definition. Geometrically speaking, what's going on? Let's go back to our notion of these balls inside of these particular spaces. The idea here is this. Let's say that you are looking at a ball of radius delta in your domain space for this function f. So it's centered here at the point A. So that's what we're kind of taking a look at. We're saying this function is continuous at the point A. Then we could go through and look to see where this function gets mapped toward. Well, where is it that we're going to be able to map this function? Notice that what you get from mapping over a ball from one set to another may not be a ball at all. It may just be kind of this little oblong set, something like what we have going on in this little dotted region. So that is the dotted region here, to be specific. That is the set f of b of a delta. And notice that what we want that to happen is essentially everything that is inside of that set of f of the image of the ball of radius delta around the point A, we want that to be inside the ball of the radius epsilon at the point f of A, right? That's what essentially is being meant by the idea that d of f of x, comma f of A is less than epsilon. What is this f of x? It's an element inside of this set. X here is something that is already within delta of the value of A. So the geometric formulation looks a lot like this. And you're taking any particular epsilon ball in the codomain around the point f of A, then there exists a small enough ball inside of the domain around that can be a radius delta, so that whenever you map anything inside of that ball, it gets mapped into this ball of radius epsilon around the point f of A. So this is our geometric formulation that we will see from time to time again. The sequential definition of continuity that we expect from RM is also something that we can carry over to the notion of metric spaces. See in this proposition that we can say a function f is continuous at a point A if and only if whenever x of n converges to A, f of x of n converges to f of A. This is why we talk about convergence before we get to continuity. We can now build in the notion of convergence that we're familiar with in the continuity definition sequentially from the real numbers and build them into metric spaces in a very similar way. Notice that this proof is a two-directional proof, and I want you to be looking at this proof and noticing a lot of connections between how this proof is written and how we wrote the sequential definition of continuity proof back in week 2. Notice here, for example, when we're going from f being continuous to A to the sequential definition, we start by saying let f be continuous at x equals A, and to consider the limit as x again as it approaches A. Then for epsilon greater than 0, there is a delta such that whenever you take this this delta is going to be less than epsilon whenever this is less than delta. So whenever you take x sub n to be going toward A, there's going to be a cutoff point such that you're eventually in this delta neighborhood. And hence, you're going to eventually be in this epsilon neighborhood as well. So you get a lot of the same sorts of pieces as you would like for the definitions of the f of x of n converging to f of A in terms of this epsilon. Notice that in our formula here, because we got to use the fact that x of n converged to A, we got to choose what this value of stand-in for epsilon was in terms of the definition of convergence for the sequence x of n. And we chose that epsilon to be equal to delta in this case. Then, using the fact that whenever d sub x of x comma A is less than delta, we get a similar thing in terms of the image, this time in terms of less than epsilon. We ended up finding the less than epsilon argument we were looking for at the very end of this argument. Namely, we've shown that f of x of n converges to f of A as we desired. In the other direction, we similarly to the last one are assuming that f is not continuous at the point x equals A. So there's going to be some epsilon greater than 0 such that for all delta greater than 0, there is some x so that the distance between x and A is less than delta, while the distance from f of x and f of A is greater than or equal to epsilon. So we are just going to say, fixing that epsilon, take these delta sub n values to be equal to 1 over n, so that eventually you're getting a sequence x sub n that has this distance property while the y values cannot have the property that f of x of n converges to A, f of A. And that's going to mean that we cannot get this notion of continuity to work in this case whenever f is not continuous at A, so that these two notions are equivalent indeed. Let's prove that an isometry between two metric spaces is continuous. This one's an interesting problem. Isometries, remember, are the fact that if you have a function, then the distance in terms of y between f of x and f of y is going to be equal to the distance in terms of x between the points x and y. So This is saying that when you map something through these functions, that the distance between f of x and f of y is exactly equal to the distance between x and y. Now, this sort of equality is actually going to get us really close to where we want to be, isn't it? Because what is it that we want to do? We want to show either a sequential definition continuity, saying that if you have a sequence of x values such that this distance grows small, then this distance grows small. Or we want to do an epsilon delta proof, which says for all epsilon, there exists a delta, so that whenever these values are within delta, these values are within epsilon. But we get a lot of help here, which says that distances in the metric space of x are equal to the distances in the metric space y. These are exactly the same distances. So either definition of continuity is okay here. And that is either the epsilon delta or the sequential. Here is how maybe we would do it in terms of the epsilon and delta proof. We could say fix epsilon greater than 0, then if dxy comma is like this, if this is less than epsilon, then d sub y f of x comma f of y. In fact, I need to say that it's maybe continuous at a point A. So let me actually give a point A here instead, so that this is kind of more in line with how that definition works. It's a little bit easier now to see where things are coming from. Then the distance from y between f of x and f of a is equal to, and this is by the fact that f is an isometry, the distance in x between x and a is also less than epsilon. Notice that I never needed to define a delta. It was okay for me to just write that delta to be epsilon for this. And the reason behind that is distances in x are equal to distances in y. So this is it. This is the proof. We fix epsilon greater than 0. Then we say, well, that's an arbitrary one. There exists a delta. Here, my delta is epsilon. So just as a quick note, we are letting delta equal to epsilon, so that this is true. Although we don't need to say something like that, it's good for us to reference it and just to make clear what's going on there in that point of the proof. Then the distance in y of f of x and f of a is equal to the distance in x and a due to the fact that f is an isometry and this is less than epsilon. Something that's very helpful for your proofs are these little things right here where you are specifying the reason behind some of your equalities. You see me do that a lot in some of my proofs, especially those that get a little bit more complex. For proofs even like this, my recommendation is to write these little hints, these little guidelines to say, here's where this equality comes from, or this is what I'm doing here. I'm letting delta equal epsilon, wherever you see them being relevant. Not only is this going to help the grader understand what's going on in your homework problems, but it's also going to help you come back to this problem and be like, why did I even say that? You're going to be like, oh, okay, because you're probably be more familiar with the definition of continuity than that of an isometry. So you're saying, okay, here's where I used isometry. Here's where I used that I'm just letting delta equal to epsilon. And that makes a lot more sense when you're coming back to this, and maybe some of these definitions are not as comfortable to you later on. Here's another interesting problem. Let's prove that any function from the natural numbers to the real numbers is continuous. Start there. Any function that you could form at all from the natural numbers to the real numbers is continuous. And this is by kind of our definition here of continuity. So think about this. Let's maybe use the sequential definition to help us out with this one, just to switch it up. Then let's think about this. You're going to start by having sequences, let x sub n converge to a in the set of natural numbers. And the question that you probably immediately ask is, with respect to what metric? We know what the metric is in terms of the real numbers, so what metric are we using here in terms of the natural numbers? Well, notice that the natural numbers are a discrete space. So one thing that we could use is perhaps the discrete metric. Typically, whenever we're looking at a subset of the real numbers, we're going to be using the relative metric. So let's go ahead and say that this is in the relative metric that the natural numbers n inherits as a subset of R. And indeed, that is what's implied here. Whenever you're taking something like the natural numbers, something that is a subset of R, then you're using that relative metric. Remember, a couple of times ago, we were looking at how you can always say that a subset of a metric space is itself a metric space. You just have to give it the exact same metric. Well, so now say that the sequence x of n converges to some natural number a. What has to be true about that sequence? Well, I also gave some intuition here about the discrete metric, this being a discrete space, which is that x of n must eventually equal a. And something that might be helpful here if you're writing this is to say let epsilon equal 1/2 in the sequential definition of continuity. Or you could even say this is the epsilon delta definition of continuity at that point. So that you're basically saying that eventually, in order for x of n to approach a, or rather, this is just in the, actually, this is in the definition, not in the continuity, because we're just talking about x of n approaching a. We're saying let epsilon equal to 1/2 in the definition of convergence. There we go. So let epsilon equal 1/2 in the definition of convergence is a good enough explanation as to what's going on there. X of n must eventually equal a. Perfect. So what does that mean? Then f of x of n is going to eventually equal f of a. And that's just by the sake of a function can only map one point to another point. And as we start kind of working around this problem, we start realizing that we're getting to the points that this function is continuous, isn't it? This is being an arbitrary function where the only thing that I'm using is the fact that x of n converges to a. And what we want to show is that f of x of n converges to f of a. So f of x of n converges to f of a as desired. Notice we never used any other property about the function. We just said it's a function going from the natural numbers to the real numbers. So this is just using that definition. The interesting part that I'm trying to illustrate here is that now that your spaces could be something that's not just the real numbers, notions of continuity are now very interesting. They're a little curious. They are not the same thing that you would expect them to be. Sometimes lots of functions are continuous, or like we'll see in the second sentence, the only functions that are continuous are constant functions. Here's the set of all functions from looking at a function from the real numbers to the natural numbers. Let's show that whatever is continuous here must be constant. All right, so here let's use the epsilon delta definition for continuity. This is for sequential definition of continuity. And here is for the epsilon delta definition of continuity. So here, let epsilon equal, let's do 1/2 one more time. Then there must exist, because the fact that f is continuous, there must exist a delta, which we don't know about, greater than 0, such that whenever you get that the value of x minus a is less than delta, that this implies that f of x minus f of a is less than 1/2. So what does that mean? If f of x minus f of a in absolute value is less than 1/2, what's going on here? F of a and f of x are in the natural numbers because these are now in the codomain of this function. So because their distance between them is less than 1/2, we must say that f of x is equal to f of a. Something that we have to end up with. Okay, well, what does that mean? Now we're still trying to figure out, okay, what's happening here? Show any function f, which is continuous, must be constant. What have we decided from this? That there is going to be some little delta neighborhood around this value of f of a, so that basically any x value within delta, or that is delta close of a, has constant y values. We haven't quite shown that this whole function is constant yet, though. We've shown that any x value within delta of a has constant y values. And that's because of this notion of like there existing a delta greater than 0. So then what could we do next? Well, we can do this at every single y value, right? We could do this at any single y value of this point, but then eventually we need all of these things to tie together. So let's think a little bit about how we can say that this function is now constant, not just around a particular neighborhood of f of a, but anywhere that we could be doing this. And the way that we can do that is this. We just note that the value of a, which is inside of R, is arbitrary. So even though this delta exists with respect to whatever our value of a is, it's still going to work, say, on the endpoint of the little delta ball window that you have there. So if you are on a boundary, for example, you're still going to be able to wrap all of that stuff inside of there and say that everything there is still going to be the same. Maybe one way to say that is something like this. So f is constant on any neighborhood around any point. So it's constant on, or rather, maybe more specific, better to say, instead of just trying to lie in that, is to say, so at any point A and R, there is a neighborhood, and I'll just keep kind of writing it down here on this next slide. So at any point A and R, there is a neighborhood, maybe we can call it some sort of, there's like a delta ball or something like this, which is going to be B A delta sub A around where f is constant. All right, so basically the idea is that every single open neighborhood there is going to be there, right? So now we use the facts that there is going to be a little fact here that we're going to use from our friends in topology is to note, finally, that R is connected. And that is to say, R is connected, meaning that there is no separation between any two given sets inside of this region of the real numbers, right? So for example, you might look at 0, 1 union with 2, 3, and notice that this is a disconnected set because there is some sort of dividing line between those two sets. For something like this, you might be able to show that this function f going from the natural numbers to the real numbers need not be a constant function. And that's because at this point of separation, you could actually make it constant on one interval and constant on another interval. I'll leave that to you to kind of go through and check. Instead, what we're going to say is that since R is connected, we must have then the function f is constant on all of R. So this gets us to where we would like to be. Now, there's another way to go through and do this in terms of the sequential definition of continuity here. We could have attempted going through in that sort of direction as well. Just using the fact that there is going to be a sequence, and any sequence that works neatly is going to work, is going to make that sort of thing happen. Finally, one thing that we could have considered here to maybe make this last part a little bit more clear is to attempt a contradiction proof. If it would be more convincing, show this by a contradiction proof. All right, because some of you may be familiar with the term of connected, and this is immediately, okay, this clicks with me. And even if you have seen connected, maybe you're like, oh, I would like to see a little bit more about what happens to go on there. Use the fact that the real numbers are connected, which means that if you are taking essentially any particular collection of sets here, then basically the only sets that there's no dividing line between any particular 2 points inside of this set, that there is no divider between these 2 points, that there isn't like a point A that separates all of the points here on the left and of all of the points here on the right for this notion of connectedness. This notion of connected is something that we will see from time to time coming up. It'll become a little bit more fluid, and we'll have a better definition of it once we get into next week's material, namely taking a look at open and closed sets. That's where we're kind of getting toward. There we have a very robust notion of connectedness for a set, and we'll see a little bit more in that particular direction as we get closer to there. Let's go ahead and see a few more interesting real valued functions and ask whether these are continuous. I've mentioned that we are going to see some weird notions of functions inside of this class, and one of those here is the characteristic function of the rational numbers. This is the function that is 1 whenever you plug in a rational number and 0 whenever you plug in an irrational number. You can kind of see how this function is being formed here, and if I were to continue to form it, I'd get a lot of points up here, and I'd also have a lot of points down here. The characteristic function of the rational numbers is 1 wherever there are rational numbers, and there's countably many points which are rational inside of this interval that I'm graphing this in, namely the interval from 0 to 1. Same thing if I were to graph this onto the entire real line. On the other hand, there's uncountably many irrational points here, so there's a ton of zeros here down there as well. There's kind of this sort of a balance between how to think of this function, and graphing it is certainly very tricky. The Dirichlet function is kind of like a weighted characteristic function of the rational numbers. Here, it is 0 whenever you're looking at all of the irrational numbers, or when x is equal to 0. And it's 1 over q whenever x is equal to a rational number of the form p over q, where p over q is in simplest form. So for example, you can notice here that the values of this being the value of 1/3 and this being the value of 2/3 for this function, that these 2 points are both at the y value of 1/3. So 2/3 maps to 1/3 and 1/3 maps to 1/3. That's because these are mapping just to 1 over the denominator value for each of these particular functions. I'd like to ask a quick question. Are these functions continuous? Well, I think we could start seeing that the characteristic function of the rational numbers is actually not continuous at a single point. Because any time that I think about a little epsilon window around a given point, I know that there's going to be rational points inside of that little epsilon window. And that's due to the fact that the rational numbers are dense inside of the real numbers. So using the density of the rational numbers in the real numbers, we can show that the characteristic function 1q is discontinuous everywhere. Something interesting, though, is this. We can actually take a look at something along these lines and say, well, what about the Dirichlet function? The Dirichlet function is only going to be discontinuous at any rational point. This is a little bit of an interesting type of fact. We can maybe see why these would be discontinuous at rational points, taking a look at this function here. Notice here that each of these points, even if you continue filling in parts of the graph, you're never going to get as high as 1/3 again, right? You start at 1/2, you go to 1/3, you go to 1/4, and you only get to graph maybe 2 or 3 points at each of these layers. To graph more and more as you keep going down the layers, but there's going to be a very strict separation between that particular point of the function and any other point. It kind of jumps up to that point and then jumps right back down to someplace else. However, at any irrational point, this function is going to be continuous. And my recommendation for proving something like that is try using the sequential definition of continuity. The epsilon delta definition will work as well, but I get a lot more of my intuition on this problem from looking at the sequential definition of continuity. So there's a lot of weird functions out there and a lot of things to try and play around with as you keep working through this world of metric spaces. A lot of this stuff is pretty weird. This sort of stuff is the type of stuff that kind of boggles my mind when I think about it for a long enough time. It's like trying to think about how this sort of functions are defined. Another thing that I want to mention real quick is here on this last slide is that The characteristic function here, I'm not necessarily described from what to what I'm mapping this function toward. Usually when I'm giving the students this function to senior level undergraduates, then it's understood and it's implied that what this function is going from is from the reals to the reals. But notice that this function, the characteristic function of the rationals, becomes very different if I instead make it go from the rational numbers to the real numbers. Now the notion of continuity in this function is a little bit different. I'm now looking at a function that has the rational numbers as its domain rather than the real numbers. When it's the real numbers, I definitely agree. We are jumping up and down in this function as we go across the real numbers, so this should be a discontinuous function. But what is this function when I'm looking at this? The characteristic function of the rationals defined only on the rationals is actually what? Is a constant function. This is now just constantly 1 on its domain. Our geometric intuition is now a little bit confused as to what to do. How should I be able to gauge if this function is continuous or not? I know it's a constant function, but I also know that the rational numbers have a ton of holes in them. So can I think of any function as continuous then? We probably can't think of those functions as continuous if we're thinking of them in their embedding in the functions of the reals to the reals, which is how our geometric intuition usually takes us. But if we're thinking in terms of the rational numbers being our domain, then remember what this is saying is that we're saying if Q sub n converges to Q in the rational numbers, then we want to say that 1 over Q sub n converges to 1 of Q. That basically when you map things through this function, that this is the same case, that this is something that's true in the real numbers. Notice the thing that's important here is what we're mapping things from and to inside of this set. If Q sub n converges to Q in the rational numbers versus what happens if we map them through in the codomain. That's exactly this, the sequential definition of continuity for us with respect to this example. And this should be very much true. Notice that whenever you take any collection of rational numbers and have them converge to a rational number, then this is just equal to 1. And this is just equal to 1. So yes, you're going to get that the constant sequence converges to 1. So this is actually a continuous function. So to summarize, the characters function 1q is discontinuous everywhere if our domain is R, but it is not true if our domain is Q. The function 1 sub q is just the constant function, so it is continuous. This is kind of put a little star behind the notion of relative continuity can be a bit tricky to handle. And let's go through and make sure that we're clear on that notion of relative continuity. Let's let X and Y be two metric spaces, and let's let A be a subset of the metric space X. Then a function f going from this subset A to the metric space Y is continuous at a point A and A. Oops, not on highlight. Notice here that this is now with respect to a function that is a subset of a metric space, kind of like how the rational numbers are a subset of the real numbers. If for every epsilon greater than 0, there is a delta greater than 0, such that our y values are then less than epsilon, whenever x is an A rather than an x, and d sub x is an x and A, it's less than delta. So here, remember, we're taking our values of x to now be inside of the set A rather than inside of the big set X. Remember, that's how kind of like our geometric intuition was a bit confused before. If you're looking at the characteristic function of the rationals in terms of the reals, yeah, definitely not a continuous function. But remember, we're asking for our values of our function that we're plugging into this epsilon delta definition to now be inside of this subset. And in our case, for the characteristic function from up above, that was the rational numbers. We were saying these x values need to be inside of the rational numbers in order to make this work, in which case you'd just be looking at the constant values of 1. This is exactly the definition that we used, was that we used the sequential definition that says if f of n converges to A, whenever this sequence is inside of A and x of n converges to A, then that means that the function f is continuous at that point, and vice versa. So here, to be specific, we're saying that this function f is continuous at a point A as that function would be restricted to the set A. So if we wanted to be very specific about that, we would say here f is going from A to Y. The last thing I'm going to leave us on is this definition of an equivalent metric. You may remember from a couple of slides ago, I was mentioning that we could think about the natural numbers in two different ways. We could think of the natural numbers either using its relative metric, that is, that d of nm is equal to the absolute value of n minus m. This is the relative metric from its being a subset of R. Or in terms of convergence, we could be thinking of n in terms of the discrete metric. Notice that these two metrics are different. So the discrete metric here is that d nm is equal to 1 if n is not equal to m, and 0 if n is equal to m. Notice that these two metrics here, although they are separate in terms of how they act, they also have the same convergent sequences. What do we mean? If you have a sequence S of n converging to a value of a natural number, say a value like, I shouldn't say n there, I should say something like k. If I have that S of n sub k eventually gets to be less than epsilon, then I know that S of n has to be eventually constant. But that's exactly what it means to converge in the discrete metric. Regardless of what metric I'm using, I have the same convergent sequences inside of that metric, either using the relative metric on R or the discrete metric on R. This is a notion of equivalence in between metrics. Now, the notion that our textbook uses for equivalent metrics is actually a little bit stronger. We're not going to give a name to this particular equivalence, that is, of those having the same convergent sequences, until we need it later. For now, we're going to use a slightly stronger notion of equivalence. It turns out, by the way, there's many notions of equivalence between metrics. This one is a different notion than just saying that these sequences, you have the same convergent sequences. This one's actually a good bit stronger. Here's the definition. Let's say that D1 and D2 are two metrics on the same space X. Then we are going to say that D1 and D2 are equivalent if there is a constant m such that you get that the values between any 2 points in the terms of the D2 metric, that distance, is somehow bounded by D1, the D1 distance on that side, by a factor of m on either side. So 1 over m is going to be for one side and m on the other side. That D2 somehow fits within that measure, regardless of the values x and y. This choice of m must be true, must hold true, regardless of the values x and y, which is what makes this a little bit of a tricky definition to try and make work, is that sometimes you're not going to be able to show this for given metrics, and sometimes you are going to be able to show it. An example that I had to change and alter, you can see I've got my little white boxes around. I had initially said D1 and D2 were equivalent metrics until realizing, oh wait, this is not with respect to this definition of equivalence, not actually two equivalent metrics. You may have seen a different definition of equivalence that is maybe a little bit weaker than this one. These two metrics here, D1 being the standard metric on the space R, and D2 being this bounded metric that we've been talking about before, let's show that they have the same convergent sequences, but are not equivalent metrics. After this, I'll ask you to do as an exercise to show that D1 and D2 do not have the same Cauchy sequences. That is, I'll ask you to find a sequence that is Cauchy in the D2 metric that is not Cauchy in the D1 metric. Hence, although they have the same convergent sequences, they do not have to have the same Cauchy sequences. And that is an important distinction for us, especially when we come up into our next talk for this week, which is going to be on, or the second talk of next week, which is going to be on completeness. We're going to be able to say, okay, if you're given an equivalent metric and another equivalent metric, am I getting a completion of the space that is about the same? So we'll talk a little bit about that as we start getting closer to that, as looking at completions of metric spaces, again, to help very much flourish our notion of geometric intuitions behind these sorts of spaces. So let's start here. Let's start with finding convergent sequences, or rather that they have the same convergent sequences. That is, we want to show if S of n converges in xd1, it converges in xd2, and vice versa. So we want to be able to say both directions here. Well, if absolute x minus y goes to 0, or rather say, let's say absolute value of s of n minus s goes towards 0, which is d1 s of n comma s, then d2 s of n comma s is going to be equal to what? We're going to have absolute value of s of n minus s divided by 1 plus s of n minus s. And notice here we are using the fact that you can take the quotient, right, a limit of quotients, and make it the quotient of the limits. So this is going to be going toward 0 over 1, which is equal to 0. So we're good on that front. If something converges in D1, then it's going to converge in D2. So this is by quotient of limits. All right, so we've got that one down. Nice. Let's take a look at this other direction because I'm a little curious on this one. What's going to happen for this other spot? What if we're looking at, what if we're looking at if d2 Sn comma s, which is equal to the absolute value of s of n minus s over 1 plus absolute value of s of n minus s, what happens if this goes to 0? Right? Well, there's kind of an intuitive notion as to why this is true. Because we're seeing a fraction go towards 0, it needs to be the case that the numerator goes towards 0, right? Because this, regardless of whatever our denominator is, we're going to get that our numerator needs to go for 0 for this. And in fact, we get a neat little way of showing this, which is this. If this goes towards 0, then how can we connect to s of n minus s, just the value of s of n minus s, right? Is there like a less than or equal to relationship with something like this? Well, no, there's not. There's not quite a less than or equal to here. But there is going to be maybe a point in which this numerator becomes so small that, yes, you could say that maybe this is less than or equal to 2 times this. And if we could get to that point, then we would be good to go as well. So let's think about when it would be the case that we're able to say that. Maybe there's going to be a time in which maybe I can't say, okay, this thing is less than or equal to this, but maybe this over 2 is less than or equal to that. Is there a way for us to make that work? Well, we would need to have it be the case that, in this case, s of n minus s needs to be less than 1. Well, then what needs to be true about the absolute value of s of n minus s over 1 plus absolute value of s of n minus s in this case? Well, what is this going to be less than? Maybe this is less than something like 1/2. We would have to check to see if that ends up being true. So we can go through and take a look at this value of t over 1 plus t and note that this is an increasing function. So in order for this value, t, whenever t is less than 1, we can just look to see what happens whenever I plug in t equals 1, in which case I would have 1 over 1 plus 1. So this would be 1/2. So this kind of counts as our scratch work. Then we can now say we're going to focus on the values of n such that there's an n greater than n implies that absolute value of s of n minus s over 1 plus s of n minus s is less than 1/2. Then we have that s of n minus s over 2 is less than or equal to absolute value s of n minus s over 1 plus this absolute value here. And we can do that based off of our work from what we've seen before. Since absolute value of s of n minus s must also now be less than 1, which implies, since this goes towards 0, we have that d1 s of n comma s also is going to go towards 0. So this gives us what we're looking for. We have kind of a little bit of scratch work here that I'm going to go ahead and erase just for the sake of getting to a little bit more room for what we need to write. And then I'm going to take this and scrunch it all up over here. There we go. Make that a little bigger for us when we come back for it. Then divide those up. And then, so now that we've shown that these two are the same type of, I'll write this to make it a little bit bigger now that it's scrunched up. Now that we've written this so that's D1 goes to 0 implies D2 goes to 0, and hence and also D2 goes to 0 implies D1 goes to 0 for these particular sequences. So D1 S comma S goes to 0. We now want to show this last part, which is that these two things are not equivalent metrics. So let's see if something like that is possible. Well, what is our intuition on this part? What's our intuition here for two equivalent metrics? My intuition says this. I remember us talking about D2 being a bounded metric, whereas D1 is definitely not a bounded metric. You can make those values of X and Y grow to be very big. So maybe there's a way to kind of exploit that, right? So in order to show these are not equivalent metrics, we need to be able to show that for all values of M, whatever they might be in the real numbers, that there exists X and Y inside of our set X, such that, this is what we want to show. We want to show that there exists X and Y inside of the set X, such that the distance to X and Y, either that this breaks this side here, or that d2xy is greater than or equal to m times d1xy. Okay, so we're trying to show either one or these other inequalities, because to show that these two things are equivalent, we need to have both of these being the case. And now we want to try and show that for all m, there are some x and y that make this break. Let's think. I'm going to use this fact. I'm going to use the fact that I can make the distances between these as large as I would like. And the distance, note that d2xy is always less than or equal to 1. So I'm going to try and just say, okay, well, is it possible for me to take values x and y inside of the set x such that, and here I'm using this left-hand part, so I'm going to make a little connection here. So if I'm taking this part and using the fact that this is 1 over m d1xy, if I show that this is greater than or equal to 1, then I've shown that it's greater than or equal to d2xy by combining these two inequalities together. So let y equal 1 or y equal 0, and let x equal m plus 1. Right? And so combining everything there tells us, okay, well, the only way that you could make that work is if you are able to find something that breaks any single bound that you have. And we get to say for all m in the real numbers, regardless of what that m is, that there exists x and y such that the distance between x and y is greater than or equal to that m, while that distance between x and y and d2 stays at 1. And that shows that these are not equivalent metrics. By the way, you could use that as maybe the start of a sequence that is Cauchy in D2 and not in D1. So I recommend trying to take a look at that direction there for this if you're interested. I'll go ahead and take a look a little bit here and try and make some of this stuff neater, since we had to kind of make a little bit of our work smaller. Goes to 0. Then there we go. So now we have finished what we needed to talk about. Excellent. Once again, gone through a good bit this time. Talking about continuity in terms of metric spaces. We've talked about continuity in many different contexts, not only just relative continuity and continuity in terms of epsilon, delta, and sequential. We've also seen it in terms of the Cantor function, right? And in terms of all these other types of examples that we've kind of gone through, looking at functions going from n to r, functions from r to n. These all help to kind of break some of the intuition that we usually get from working in just the real numbers. Our notions of continuity are now a little bit wonkier than they were from before, because our spaces are a little bit wonkier than they were before. Finally, we've talked about equivalent metrics, about how to show what two equivalent metrics are equivalent, and we'll see that equivalent metrics actually can be characterized by something that I'm hinting here in this exercise, which is that equivalent metrics not only have the same convergent sequences, but they also have the same Cauchy sequences. And you can kind of use this definition up here to check to make sure that that ends up working. But that'll do it for me today. Thank you so much. Have a wonderful day.